With the Lucky Land Slots, you can get lucky just about anywhere.
This is your captain speaking. We've got clear runway and the weather's fine, but we're just going to circle up here a while and get lucky. No, nothing like that. It's just these cash prizes add up quick. So I suggest you sit back, keep your tray table upright, and start getting lucky.
Play for free at LuckyLandSlots.com. Are you feeling lucky? No purchase necessary. Void where prohibited by law. 18+ terms and conditions apply. See website for details.
Okay, round two. Name something that's not boring.
A laundry? Ooh, a book club. Computer solitaire, huh?
Sorry, we were looking for Chumba Casino. That's right. ChumbaCasino.com has over 100 casino-style games. Join today and play for free for your chance to redeem some serious prizes. ChumbaCasino.com. No purchase necessary. Void where prohibited by law. 18+ terms and conditions apply. See website for details.
Hey, Breaking Math fans. First, I want to thank you for listening. I have an important message for everyone. You can start your own podcast right now with Anchor. Anchor lets you create and distribute your own podcast. Just get an idea, record, and upload. It's just that easy. Anyone can do it. I'm on my way to accomplishing my dream, and you can too. Just get on your device's app store and download Anchor. It contains everything you need to make a podcast. With Anchor, you can put your podcast on all the big platforms. Apple Podcast, Spotify, Google Podcast, Amazon, and more. Reach the whole world with Anchor. Best of all, Anchor is free. You have nothing to lose with a free platform. Download the Anchor app or go to anchor.fm to get started.
Herein lie a group of mathematical problems that have analysis, not intuition, at their core. What we mean by this is that these problems are counterintuitive, but are, by any stretch of logic, correct or incorrect. These problems will include the birthday paradox, a common mathematical fallacy, the shape of Gabriel's trumpet, and the gambler's ruin. We present this episode in the hopes that you enjoy the challenge that they present. We hope you enjoyed this mini-sode. I'm Jonathan.
And I'm Gabriel.
And what's the first paradox or weird question that we have today?
Very first paradox is actually one that I just read about recently, and I suppose it's well known in some circles. It's called the birthday paradox.
Yeah, and let me state the exact question. How many people do you have to have in a room in order to have a 50% chance or greater of any two sharing an exact birthday with one another? Exact birthday meaning month and day and not necessarily year.
This one absolutely blew my mind. I had my guess. I went about trying to solve it, and then once I saw the solution, I was completely wrong. So I'm hoping to find out if some of our listeners can empathize with me and see if I'm not the only one who gets this wrong.
And we're going to show you the math behind it later, but first we want you to use your intuition. Is it 1 out of 365, n out of 365, where n is the amount of people in the room, greater than 100, greater than 50, or greater than 20, or less than 20, I guess. So you have a few options there.
Okay. That sounds like 5 options that we're going to give to our listeners, right? And should we just say it one more time?
Sure. Is it 1 out of 365, n out of 365, where n is the amount of people in the room, greater than 100, greater than 50, greater than 20, or less than 20?
Interesting. Okay. And of course, in this case, one of the numbers, of course, is within a year there are 365 days. We are not counting leap year here.
So now we're going to continue on to the next paradox. This one is a simple one. What is the sum of 1 plus negative 1 plus 1 plus negative 1 plus 1 plus negative 1 ad infinitum?
Now, didn't this particular problem that you just mentioned, I think this has an origin with the mathematician Friedrich Gauss. Is that correct?
I believe it does. I would have to look that up to make sure. But if it does, I wouldn't be surprised. Gauss is one of my favorite mathematicians, and this is right up his alley. Interesting.
Yeah, that seems like such a simple problem. But it's, again, with the theme of our episode, it may not be what you expect. So again, it's we're starting from, you do a summation from n equals 0 to infinity. Is that correct?
Yes.
Okay. And then it's just 1 plus -1, et cetera, et cetera, et cetera. And then what is the final answer?
And that is the question.
And then, so we'll give you a while to think on that one. We're not going to go over the answers yet. We'll go ahead and introduce you to the third problem that we're going to discuss on today's minisode. The third one is called Gabriel's Trumpet. And of course, I'm not referring to myself here, although I was named after this Gabriel. This is the angel Gabriel. It's called Gabriel's Trumpet. And Jonathan, do you want to explain why this problem is called Gabriel's Trumpet?
Sure. There's a shape called Gabriel's Trumpet. And what it is you can imagine the graph of 1 over x. That's to say that at 0, it's infinity. At 1, it's 1. At 2, it's 1/2. At 3, it's 1/3. So it's 1 over whatever number it is.
And if you're looking at that graph, of course, it looks like a trumpet. It starts high and it curves downward, and then it asymptotically approaches 0.
Or at least the profile of the trumpet. And what Gabriel's trumpet really is that surface being revolved around the x-axis. So let me break this down for some of the people who might have trouble visualizing graphs. You have this shape that goes really high up and then really far down and then almost approaches 0. You take that and imagine a lathe. A lathe is a thing that you make baseball bats on. But imagine you're making a trumpet out of the baseball lathe, where the open part is infinitely large and then it trails off into this very, very tiny shape. What we're asking about this shape is what's the surface area and what's the volume?
This last problem is referred to as the gambler's ruin. And once again, Jonathan, would you like to introduce this one?
Sure, I'll introduce it with the simplified version because the full version is a little bit complex and I think that it doesn't add anything to the understanding of this.
Okay.
Let's say we're playing a game and you have a 50% chance of winning every time. If you win, you get double the money, and if you lose, you get none of the money. What's the best way to play this game? And is there any way to play this game with a finite amount of money and not get broke?
Interesting. Okay. So, and then basically when we talk about strategies, obviously it's a simple game of chance, and you basically do a fraction of the money that you have for each win. Is that correct?
Yes, but that fraction could be and you don't have to invest half of it. You could invest twice as much. We're assuming. So like if you do $1 on the first one, you could do like $40 on the second one or something like that. We're saying what's the best strategy. And we're going to give you a second to think about that. So if you'd like to work on these problems by yourself, you can pause right now. And we're back.
Alrighty, at this point we get to go over these 4 problems, and you can see if you were correct. So I think the first problem we were talking about is the birthday paradox. Before we give you the answer, let's talk about that problem one more time, shall we?
Yeah, how many people do you have to have in a room in order to have a 50% chance or greater of 2 people in that room sharing an exact birthday with one another?
Okay, and I think we actually gave you a choice of was it 4 or 5 options here. What in the first option I think was is it a 1 out of 365 chance? Is that the correct answer? What are the other options?
N over 365, where N is the number of people in the room, greater than 100, greater than 50, greater than 20, or less than 20.
And the final answer is, drumroll please.
Well, before we get that, I'm going to belay your drum roll.
Oh, okay.
I'm going to give you a way of thinking about this problem in case you want to pause one more time and you didn't get it the first time. What's the chance of 2 people not sharing a birthday?
Oh, yeah, that'd be a huge, huge chance. So if you just start with just 2 people in a room, then there's a huge chance of them not sharing it.
Yeah, in fact, it's 365 over 365 times 364 over 365. And I think that's giving you enough of a clue. So if you want to pause now. And for some of you, we are back. For other of you, we are not. And the answer for 365 different days is 23. You only have to have 23 people for there to be a greater than 50% chance of two sharing a birthday.
I got that completely wrong the first time I did it, and honestly, I don't think I had a real strategy in mind. I just thought how many people would I have to have for myself in order to have some chance of somebody being born on my birthday. And of course, that was part of my first problem. It's not only about me, it's about any two people at all.
Yeah, in fact, the answer is completely different. If you want to say how many people would you have to have in a room to have the same birthday as you, the expected number would be 365.
Yeah, but then it changes when you consider any two people at all. So this is a great lesson, I think. I think that statistics in general are very important, for all kinds of reasons, and this gives you reason to really carefully consider the information that you're given when somebody is rattling off stats.
Now, how many hours are there in a year, Gabriel?
There are in a year, if we did some quick calculations, I want to say 8,760.
And so how many people would it take for two people to share not only the same day of the same month for their birthday, but the same hour of the same day of the same month?
Ooh, do you want me to just guess here? I'd be happy to just hazard a guess here. It seems like a very low probability. I know it's 23 was the first answer, but if we if we make it a little more complicated, and they're still out of 24 hours, so we're going to increase it. It's going to be more than 23. I know that.
Oh yeah, and we're dealing with a number that's about 30 times as big as 365.
Yeah. Now, I know that you already gave the formula away, so solving it really isn't too tricky. Do you want to say the formula one more time?
Yeah, the formula is 365 over 365 times 364 over 365, and you keep doing that until you get 365 minus n over 365, and that total number is less than 1/2. And then that's the chance of those people not sharing a birthday, so the chance of them sharing a birthday is 1 minus that.
Okay.
So
and then to add the extra element of sharing the same hour in the day.
All you have to do is multiply 365 by 24 and plug in and do the same thing over and over again.
Okay. Yeah, actually, and the answer to that one is you need 111 people. Can you believe that? So how often are you in a room with 111 other people? Like at a small concert or like maybe a high school play. So there is there's approximately a 50% chance that you share not only the same birthday but the same hour as somebody else. In fact, I remember in my high school theater class, there were two people who I shared the same birthday with. That was pretty remarkable.
And seeing from your end, that's even more remarkable. From the end of the teacher, that's not as remarkable. And that's the interesting thing about statistics, is all about perspective.
Oh, that's right. Yeah, good point. Wow. We should do more probability problems. I like these.
And the last one is the exact minute of the exact hour of the exact day of the exact month. 525,600 possibilities. And how many people do you have to have in a room for that, Gabriel? We crunched the numbers.
To have the exact minute, the exact hour, and the exact day, you'd have to have 854 people to have a 50% chance of that happening.
That's all. So it does not increase in proportion with the number, because that's 60 times as large as the number before.
That's like a medium to small high school in certain towns, 854 people.
Yeah, I mean, I think I went to a high school with about 1,200 people.
Wow.
And so there's a greater than 50% chance of two people sharing the exact minute.
Wow, that's crazy. So really, if you just say that you're a superintendent and you visit a whole lot of high schools, there's almost well, I guess you wouldn't say that there's a guarantee that eventually you will find a person who meets this, but
in fact, quite the opposite. It's much less likely.
Yes, again, that's a problem of perspective. But the likelihood of finding two people, any two people who share the exact minute, the exact hour, the exact day of any two people, that you still only need 854 people. That's quite remarkable. All right, so should we move on to the second problem?
Definitely. So what's 1 plus -1 plus 1 plus -1 plus 1 plus -1, etc.?
And the answer I'm going to say is, well, it depends.
It does depend, because what's 1 plus negative 1?
0.
And then what's 1 plus negative 1?
0.
So then if you keep grouping them like that, you get 0 plus 0 plus 0 plus 0, which is always what?
0, of course.
However, if you group them the other way, like this, 1 plus negative 1 plus 1 plus negative 1 plus 1 plus etc., you get 1 plus 0 plus 0 plus 0, which is...
a final answer of 1.
So it could either be 0 or 1. So the solution to this is that these are illogical because they do not converge.
Yes, so we threw you guys a curveball, and, part of me was like, should we apologize to our audience for throwing them a curveball? I don't know. I don't think so.
No, we shouldn't.
Yeah.
And what's interesting about this is that the way that you kind of formalize it is that you have to say there has to be, for every epsilon, meaning like a number epsilon, there has to be a number n, such that the nth thing in the sequence and beyond, the difference between any two of those is less than epsilon.
Interesting. Now, is there a more modern English way that you could phrase that?
Sure. There has to be for every little number, tiny number, there has to be a point at which any two subsequent elements of the sequence are less than that tiny number.
Now, if you were to do one of those, what's the expression if you're reading on Reddit and somebody puts, is it TLDR? Too long, didn't read. The TLDR of this would simply be, for some problems, it depends on how you group it.
Or you could say that if it depends on how you group it, it's not a valid problem.
Indeed. And then we've got the next problem we introduced you to, which was Gabriel's trumpet. And we talked about the shape of the trumpet, which, if you see a trumpet sideways, or rather part of a trumpet, the horn part, and then what was the two bits of information that we were...
Well, the graph is that of 1 over x, meaning that when you start at the mouth of the trumpet, it's infinitely large. Let's say we're measuring it in feet. If you go like 7 feet down the trumpet, it's only 1/7 of a foot in radius.
Okay, right. And then I think the two things that we're asking for was the surface area, and was it the volume?
Yep, and the volume is pi.
Interesting. Yeah, that's really cool. I like how often pi shows up.
Yeah, and you could prove this with some very simple calculus. If the phrase simple calculus seems like an oxymoron to some of you, then just you could take our word for it, or you could find some very, very good explanations online.
Yeah, and then we know that the volume is pi, or pi units, whatever units those might be. Now, it would be volumetric units, right?
Yeah, so it'd be units cubed.
Okay, and it would be pi cubed. It would still just
no,
pi.
it would be
Yep.
pi units cubed.
Indeed. Now, the next question was the surface area. So what is the surface area of this shape?
It is infinite.
Infinity. So it's quite interesting that you can have something that has a very, that has a finite volume, but an infinite surface area. That's mathematics for you.
And so if you think about it, you could increase the shape of Gabriel's trumpet. Like, let's say you're trying to gold plate it. You can increase the shape of Gabriel's trumpet and get a gold plating, but as the farther you go down, the thinner the plating would be. So to plate it evenly, you would have to have an infinite amount of gold leaf.
And then we've got one last problem that we introduced you to, and this was the gambler's ruin problem. And this problem was asking you to devise a strategy in a game of chance in order to have the best outcome for you. What were the other details of this particular problem?
You have a 50% chance of winning. And if you win, they give you twice the amount of money. If you lose, they take all your money. So it's basically a double or nothing.
Okay.
With a 50% chance.
Okay. Very good. Very good. Alrighty. And we said, is there a way to have a surefire way of winning this or any gambling challenge?
Yes. If you have an infinite amount of money and the casino lets you bet an infinite amount of money at any given, or an arbitrarily large amount of money at any time, all you have to do, so if you start off with $1, let's say you lose, right?
Okay, so I lose.
All right, so you're down $1, so bet $2, and then if you win, you're up $1. So then you lose. And if you continue this, the most you can expect to win is what you started with, $1.
Okay. And that's only if I can bet an arbitrarily large amount and an infinite amount of times.
Yes, and what I mean by expect to win is I mean the expected value of your winnings, which is a slight difference. I would look up expected value. It's a very complicated concept which we don't have time to go into. But one thing that really threw me for a loop when I first heard this problem is I would think, okay, let's say I'm up by $4. Why can't that be my starting point? And why can't I expect to win $4 and then $8 and then $16 and so on? And the reason why is because of the law of large numbers. You're always going to get back to where you started. Interesting.
So yeah, and actually, I'm not even familiar with the law of large numbers myself. So there's something that I can certainly research as well.
The simple version of the law of large numbers is that if you flip a coin an infinite amount of times, you're going to get about half and half.
Oh, got it. Okay.
And the complicated version is that the sum of any set of random variables is going to approach a Gaussian, but we're not going to go into that.
Okay, alrighty. And then the other question I have on this particular problem is there a surefire way to lose all your money?
Yes, have a finite amount to start with. Because you can be up and down, but there's going to be a point where you're trying to win and you're going to not have enough money to bet double. That's to say you might be down $65,535 and you're trying to bet $65,536 to win your original dollar back, but you don't have that. So that's how you lose, and you will eventually always lose.
Well, that has been our four challenge problems for this week's minisode. We hope you enjoyed it.
And until next time, ruin some gamblers. Don't do that.
And the minisode's over, but we want to talk to you about our upcoming show.
We are absolutely ecstatic about a very, very long podcast episode that we just recorded that we are in the process of editing. So we thought we'd give you a nice little teaser about this one. Jonathan, are you excited about this one?
I am. We talk about artificial and natural states of consciousness and how they can be altered.
Yes, altering states of consciousness. We have a very special guest on the episode. The guest he's been diagnosed with the condition schizophrenia, and he really tells the listener a lot about what it's like to have this condition, what he experiences, and also some really insightful things for those who don't have it that we could possibly benefit from knowing.
And we also have a guest who has had substance use in his past. We interview him about that, the experiences that he's had, and it's not the most mathematical episode that we've ever done, but it's part of a 3-part series.
That's correct. Now, actually, about the math, my idea is that anything that can be described has a mathematical element to it, so that's my argument. And again, we can get more into the math and the relationship between parts of your brain and consciousness. But more on the episode, we hit on so many things. We talk about hypnosis. We talk about dreams. We talk about, the evolution of creativity and inspiration and what that has to do with consciousness as a whole.
We even talk a little bit about Gabriel's trip to Mexico. And we are going to talk a little bit right now about, I thought it'd be cool to just talk to you about a mathematical theory of mental illness that treats it as a graph. Gabriel, do you want to introduce them to what a graph means, speaking mathematically?
Well, let's see. So I think that we'd have to start off with what a normal conscious experience would be, right?
Oh, yeah. But I mean, I think we should introduce the concept of just graphs. What do you think?
Sure. Yes. So obviously, basic definition of a graph, an XY coordinate grid that we all learn in 5th grade or in middle school, where you just plot points according to an equation. It's pretty well understood.
And that's a popular notion of a graph. There's another word, and it's very confusing, and the guest found it confusing on the episode about a graph, is that a graph is also a set of nodes connected by arrows or lines.
So I was wrong.
No, you're both right.
Okay, that was very polite, John. That's a very polite way of you saying, not quite, Gabe, not quite.
But yeah, so there's this theory that mental illness is different than physical illness in the way that it can be treated, because with mental illness, if you really think about it, you might only have symptoms in certain cases. It's not the least controversial thing, but when you're treating symptoms, a lot of times you could treat groups of symptoms, and if you treat them as groups that can be looked at under this graph, you could use certain illnesses based on the shape of the graph. So think about it like the shape of the internet. If the shape of the internet represented an illness, then you'd treat it based on if you're on a very link-heavy site like Wikipedia, or if you're on a very content-heavy site like Huffington Post. Not Huffington Post, but something like that.
Interesting. Wow, yeah, there's a lot of really cool ways of describing. Oh, and I wanted to say one other thing. I also talk about a personal story of a family member that was diagnosed with severe bipolar disorder and was very successfully treated with electroconvulsive therapy. I'm not going to say a whole lot here, but be sure to tune in next week for that episode.
And I reveal something personal about myself. But so this has been the end of the mini-sode that wasn't part of the mini-sode. This page intentionally left blank.
Very good. We'll see you guys next time.